Then we have Agniva telling us about anchor embeddings.
All right, so thank you for the invite, Leah. Thank you all for being here. So I'll talk about these objects called anchored symplectic embeddings. And any theorems I claim as just joint work with Michael Hutchings, Weiler, V1, y'all. Okay, so just to set the stage, the original sort of the motivating question that has sort of fueled a lot of research is this question of symplectic embeddings. The way that works is you have two symplectic shapes, and you ask, when does one fit inside another? Which is an embedding which preserves, it takes the symplectic form. And so there's been some work on this, and I'm going to focus on this result, which was first conjectured by Hofer. This was about ellipsoids, and the main objects we'll be looking at, like interest, will be different symplectic versions of the four balls. That's the shapes we will consider. So we look at the four ball, which is and then similarly define the polydisk, which is product of, and then these are ellipsoids. Now we're out of space, but ellipsoids are defined similarly. And instead of C, you would have 1. So those are the shapes we will be interested in, and then something more general, which I'll define in a bit. And so the Hofer conjecture was about, well, when do ellipsoids fit inside each other? When? And the conjecture was that it only happens when a certain number theoretic condition is met. And I won't define what this number theoretic condition is, but it was resolved by work of Duff and Schlenk and Hutchings. And then finally, McDuff said that this is exactly true, that when this number theoretic condition is met, ellipsoids embed inside each other. What was striking about this is that, so what might be interesting takeaways that I will make more precise is that sometimes these conditions are strong even when volume obstructions are not there. So embeddings do not exist in some cases, even though volume obstructions vanish. And then conversely, they seem to exist in some cases even when we can't see them. And I'll make that precise. Exist even if we cannot see them. leave that space. And so what prompted this project is to ask, well, can we probe these embeddings further and sort of understand whether symplectic surfaces can exist in the space between the embeddings? And this can be thought of. And so an anchored symplectic embedding asks, can you have a symplectic embedding along with anchors? So you have alpha and alpha prime are, let's say, transverse knots in partial x prime. So they're transverse with respect to these contact structures. And an anchored symplectic embedding is the pair from sigma, so that phi x is a symplectic embedding. And there exists sigma, the symplectic surface transverse to the boundaries, thus that boundary of sigma is alpha union alpha prime union minus. And so the schematic would be, you have your x here, and you have this whole thing is x prime. You have these knots, alpha, alpha prime, and you want a surface that exists in the cobordism with these boundaries. So sigma inside x prime minus x. So which asks, is the space between the embedding sort of, is there enough space for a symplectic surface to exist between these transverse knots? So this, the motivation came from sort of trying to ask about symplectic concordances between transverse knots. There's a lot of study in smooth topology and also symplectic topology where people explore, are there Lagrangian concordances between Lagrangian knots or smooth concordances between smooth knots or smooth links? And so a natural extension of that to the symplectic world is to ask, well, when can you have symplectic surfaces between knots in the cobordism? So that's setting up the main question we're looking at. Okay. All right. And that's the definition of an anchored symplectic embedding. And I also define something called an N-anchored embedding, which says, well, suppose you have alpha prime as before, transverse knots in partial x prime, and then an N-anchored embedding x omega alpha to x prime omega prime alpha prime is the same thing as before, but sigma has n component. So with that, I'll state theorems. Do you want to state the theorem first? All right, so before I state the theorem, let's define the space. So I'll be looking at sort of generalizations of these shapes. So these are all shapes of a certain sort. So I'll just define what are convex toric domains. And the general theme is these are nice star-shaped, nice in some sense, domains in C2. And a convex toric domain is when we consider the moment map image from C2 to R2 that takes to square by 2 square. And then we say omega is convex if the set 2 such that belongs to omega is convex. So a picture of a convex toric domain would be something like this is where the image of this moment map is for C2, and then a convex toric domain is you define a function which is non-increasing. This omega is a convex toric domain. A one word of caution is that a convex toric domain isn't a domain that's convex. It's a bit more specific than that. All right. And so with that, when you have a convex toric domain, there are some natural knots that you can see on the boundary. So you can see an unknot here. Call that E10, or this E01. And so that brings us to the results, the theorems. These are all joined with Hutchings, Roy, Weiler. Now, firstly, is suppose you have omega 1, omega 2 are convex toric domains. There exists a two-anchored embedding omega 1, E10, E01 into omega 2, E10, E01 if and only if omega 1 sits inside omega 2 as a convex toric domain. So this should be seen in contrast to like the second bullet point, which I'll make it more precise, is that in these toric pictures, you can come up with domains that don't seem to embed inside each other. But if you impose this extra condition, then it seems like it has to be that specific kind of embedding that you can see. The second theorem is, so the two anchored embedding means that you respect this order. So there's a component of the anchor with ends at E10 on either end, and a component of the anchor with ends at E01 on either end. So second theorem I would state is if omega 1, omega 2, again, convex toric domains. And then you have omega 1, E10 inside, fits inside omega 2, E01, if and only if, again, you can draw a visible surface in the toric picture. So not only should they fit inside each other, what should be true is that for a convex toric domain, we can call this to be A of omega, the point where the line hits the x-axis, and call this to be B of omega. So this condition is the same as saying that v of omega 2 is bigger than x0 plus y0, where x0 plus y0 is the point where the slope is -1. And that's the same condition, a little bit small, but that's the same condition that you can draw a visible surface in the toric picture. So those are the main results. Any questions at this point? I've set up some notation. Is there any confusion with the notation? Okay. All right. And then the plan for the talk is I'll give an idea of the proofs of these, but then actually prove a theorem which is a little more specific, but it doesn't follow from either of these, but it's in the similar vein, is that if you want an anchored embedding from a polydisk E10 into the ball BC E10, you only have it if C is bigger than or equal to A plus 1. And that's also the same kind of condition as this, is that the polydisk PA1 looks something like this. This is A, this is 1. And if you want the ball to be bigger than or equal, the C to be bigger than or equal to A plus 1, you want the ball there. And these are your E1 zeros. All right. Okay. Okay, so if there's no questions, I'll keep these up and I'll talk a bit about the ideas behind the proofs.
If you take specifically a very special unlock,
Yes.
if you can pick a different knot, much more complicated, that would ease the restriction.
So that's something we're working on. It's I'll talk about the proofs, and that's a part of the future directions we're looking at. Like we would like to talk about like surfaces that multiply cover the ends, or like even if you have the unknot, you can have surfaces that multiply cover the ends, which are a little more interesting perhaps. And you can have torus knots. So I mean, for us, like we define anchored embeddings with transverse knots, but we only look at wave orbits for now. And so like convex toric domains, you expect like all torus knots to be like give you wave orbits you can study. So we would like to say something about that, but not yet.
And just making sure, so the second result is 10 to 01? Or?
Yes. Right, yeah, 10 to 01. And so that's all about. Maybe I'll just so I'll just quickly talk about the sort of the constructive directions of these results. The constructions. This, if you have two convex domains that sit inside each other, and if you have these your E1 zeros, E1 0, then this defines a cylinder, a symplectic cylinder that sort of gives you an anchor in this embedding. Similarly, this gives an anchor between the E01s. And if you wanted an anchor between this surface and that, or this knot and that, then if you draw some, so if all this gamma, if gamma has slope bigger than -1 at all points, it lifts to a symplectic cylinder as needed. Okay. So these are the constructive directions of those theorems. Okay. Next thing to talk about. So perhaps I'll just talk about the second bullet point and contrast it with the third statement there. So the third statement says, the theorem 3 says P A 1, P 1, 0, symplectically embeds. There's an anchored symplectic embedding DC E 1, 0, if and only if C is bigger than or equal to A plus 1. In contrast, Schlenk used symplectic folding to embed. There was a more general embedding into the ball that's 16/5. Okay. And if you were to draw them out in the toric picture, this is your polydisc. This is your ball size 16/5. So they're not included in as toric domains. So there does not exist a symplectic surface inside this embedding. It doesn't exist until you make the ball large enough to 17/5. There does not exist a symplectic surface with that has boundary at these knots. Okay.
This is using like the first theorem or?
No, that's the third theorem. So the first and second theorem are more general, but they don't apply the third. Because for the first theorem, you need this condition of a two anchored domain, two anchored embedding. So you really need sort of a surface between these two knots and a surface between these two knots to conclude that it has to sit inside. And there's like in the paper, there's this, like you can relax this condition with based on some condition about the heights here.
You already can't have one surface. Actually, you can't embed.
No, so the assumption here is that you have a surface between just these. So you just have a polydisc and a ball, and you're assuming there's a surface between these two. That is not that allows us to conclude that the polydisc has to look like this. But in general, for convex toric domains, if we just assume that there's a surface between these two, it's not true that this has to sit inside. We need to conclude that there's a surface between those two as well.
Sorry, I'm saying because the third one is not saying sitting inside.
Yeah, the third theorem is saying a little bit stronger than sitting inside each other. It's saying that it has to sit inside each other, and you can draw this surface, which gives you a cobordism between.
You point at the second.
Oh, the second theorem relates to this green line.
Yes.
Yes, did you?
Do this construction ever produce holomorphic surfaces? Or?
these are holomorphic on the nose. Are these holomorphic? No, they're like round. Yeah, these are holomorphic, but this doesn't generally produce something holomorphic. But for the way the proof will go is to make them holomorphic under some perturbation. So the idea of proof. So the proofs of all three are based on these ideas. So the main idea is okay. So let's talk about like maybe theorem one is when can we say that omega one is sit inside omega two as toric domains? We can interpret that by saying that zero of the point where omega one has slope AB is less than the x and y coordinates of the points. So what do I mean by this? So this is the point on pi of partial omega 1, which has slope A over B. And I mean that at every point for all, if we can show that for all points here, where it hits slope A over B, this is smaller than the corresponding point there, then we have the inclusion of domains. So that's the pictorial idea of showing how this is. How does it translate into symplectic geometry? Well, dynamics on boundaries of convex toric domains is if you have a point like this. So remember, this is the point on the boundary where you have slope A over B. If you look at its inverse image through the moment map, you get a torus which is foliated by Rabe orbits with A over B slope. And how does this x0 plus y0, x plus y come into the picture? So at any point, so if you take this point, the slope is A over B. This corresponds to a torus that's foliated by Rabe orbits with slope A over B. And the action of these Rabe orbits, or the integral of the convex form over these Rabe orbits, is given by x plus y of that point. Action of these Rabe orbits is x plus y of omega 1. So the way we will try to show this is by saying that if you have this condition, this existence of the two anchored embedding, then for these Rabe orbits, we should be able to say that the action of that Rabe orbit for omega 1 has to be less than the equal to the corresponding Rabe orbit on omega 2. Any questions? I keep these theorems. So confused. I can write on these, right? So here. Okay. So how do we show that? The idea will be, so if omega 1 symplectically embeds inside omega 2, we get this is omega 1, omega 2. What we get here is a strong symplectic cobordism from partial omega 2 to partial omega. These from and to conventions are the from and to conventions that is used in ECH. So you have, you have a cobordism in this direction. The Liouville flow direction is this way. What that implies is that there exists a homology theory of called ECH, which I'll define, of partial omega 1. There exists a map like this. If omega 1 and omega 2 are if omega 1 equals omega 2 equals this standard complex structure, get isomorphism. And then final ingredient is that given the symplectic anchor sigma, it can be straightened and deformed to give a holomorphic curve. And so then finally, so what we get is we have alpha minus, alpha plus, some surface, sigma, that's holomorphic, and we have an isomorphism. So this isomorphism also gives us, isomorphism gives us holomorphic curves to work with. Curves to work with. Maybe a loop. So the ECH map gives us holomorphic curves to work with as well. And so the way we show, so the way we show this result about the actions of these wave orbits is by using positivity of intersections of these curves. And so finally, positivity of intersections of all these holomorphic curves allow us to conclude the theorem. So this is really a schematic of what is going on in the proofs, but that's generally the idea that you have, these are all, the boundaries are all standard contact S3s, the contact structures. So on the ECH homology, you have isomorphisms that give you actual holomorphic curves to work with. Sigma gives you holomorphic curves, and then you play around with the positivity of intersections to conclude these things about the actions. Okay, so the next plan is to I'll define ECH and then give a sketch of the proof of theorem 3. Are there any questions?
This isomorphism is from Cyber-Witten. You know.
Yeah, the isomorphism goes through Cyber-Witten, but it does, like, it allows us to conclude that there are holomorphic curves. All right. That's the idea.
In your specific case, do you know the genus of it?
They're all cylinders.
Cylinders. Then do you really need ECH, or could you use other Floer type theory to get higher in dimension?
So like in higher dimensional, we're not sure. Or maybe I'm not sure. But
Can you say the coordinate is also isomorphism?
I mean, we do use like the positivity of intersections, and I mean, even if in higher dimensions you can conclude there are holomorphic curves. I don't know if if there's enough like topological restrictions on the curves to actually say anything, but I'm not sure. So review ECH. The chain comp. So your input is some 3 manifold, the contact form. What is it called? Form. You generate chain complex is generated are orbit sets of ray orbits, sets of ray orbits with multiplicities. So it's and then if alpha I is hyperbolic, the multiplicity has to be 1. And the differential counts. There's something called ECH index, 1 holomorphic curves. So this implies that there is a relative grading on the ECH chain complex that's given by this. And so we will consider the absolute grading on generators which is given by the empty set as grading 0. That's our assumption. And so that's ECH, that's the chain complex. The homology of this chain complex is ECH. It's a diffeomorphism invariant of the 3 manifold, and it's shown to be. So this was defined by Hutchings, and then the fact that the differential actually squares to 0 was shown by Hutchings and Tau. Hutchings and Tau. Okay. And so what works for us is for convex toric domains, there's a combinatorial way to look at these ECH generators and compute their actions. So for convex toric domains, combinatorics. So you take what's called a convex integral path, which is you have some lattice. So you have some convex integral path. And so these correspond, this is also Hutchings and two ECC generators of toric domains where the action, so I'll just so given this absolute grading, every generator, every ECC generator has a grading on it. The ECH index grading is the number of lattice points inside gamma, including those on the boundary. Let's see. So this is 2 minus 1. And so the way you get the ECH generators for this is, this is the curve, the vector points along 2 minus 1. So you label this 1, 2. You label this points along 1, 0. So you label it by its, the thing that's orthogonal to it. And the multiplicity is sort of the multiple that comes up. So this has, you can see, there's 2 of these 1, 0. So the multiplicity of this would be 2. So this represents an orbit set. And you have to label each of them as E or H. Maybe if you label all of these as E, then this gives you an honest orbit set. Now, what's the action of these? The action of this, of the wave orbit E1, 2 is really, as I said here, is you look at the convex toric domain, the boundary, and the sort of x plus y of that point. Gives you the action. That's pretty quick. I don't know. Okay. So that's, so combinatorially, we can see the action of a generator and we can see the ECH index of a generator. And in the one thing I should have mentioned is when you have these cobordism maps on ECH, they preserve the grading. Maybe we can actually prove something. So we want to prove theorem 3. If you remember what theorem 3 is, I'll just remind you that if P1A, P10 has an embedding to be of C, P10, then C has to be bigger than or equal to A plus 1. And we prove that there's 2 lemmas. 1. Yes. So suppose you have the cobordism sort of omega 2 to omega 1. And under the cobordism map on ECH, you have some combinatorial generator of that sort. Map this. For combinatorial generators, we can define two things, which are the point where it hits the y-axis, the point where it hits the x-axis. And there exists a holomorphic curve with boundaries at E10 in both omega 1 and omega 2. Then we must have that y of alpha plus has to be bigger than or equal to y of alpha minus. So they're both combinatorial generators, and we should have that y of alpha plus is bigger than or equal to y of alpha minus. Why is that true? So I'm going to so this is the cobordism map on ECH. So if this is true, that means that there is some holomorphic current. Let's just assume we have some holomorphic curve with ends on alpha plus and alpha minus. And we have some other holomorphic curve with boundaries at E10 and let's call that C1. So then the linking between C and C1 has to be positive by positivity of intersections. And this linking can be thought of as the linking between their boundaries. The linking, so this would be alpha plus E10 minus linking alpha minus E10 has to be positive. And now, how does this help with that? Well, let's draw a combinatorial generator and see if we can figure out the linking with E10 from this picture. So suppose this is alpha plus, and you want to figure out the linking of alpha plus E10. So these represent, so remember that this edge represents E10, and these are Rabe orbits that are distinct from E10. So the linking between Rabe with holomorphic curves that have ends at different Rabe orbits, it's just the topological linking between them. So this is, so if this was, say, 0, 1, 2, 2, 1, these are the orthogonal. The linking for this one would be 1, the linking for this one would be 2, and the linking for this one with E10 would be 1. So 1 plus 2 plus 1. But if the end is at E10, then by asymptotics of holomorphic curves, it has to be non-negative, non-positive. So minus something. So what this gives us is that this has to be bigger than equal to y of alpha less than equal to less than equal to y of alpha plus. Y of alpha plus is just the sum of all these. Similarly, we should have that linking of alpha minus E10. In this case, we should have positive asymptotics. This should be bigger than equal to y alpha minus. So now, since this is non-negative, it implies that y of alpha plus should be bigger than equal to y of alpha minus. So that's the first lemma. If you have this, you must have
So you must prove something that says your curves asymptotic. They don't have asymptotic linking.
I'm sorry? So in this part, you can have asymptotic linking, but that has to be negative. Because the winding numbers should be negative. This is the positive end.
Right.
And then in these one, the asymptotics are their distinct wave orbits. You link in with E10. This is E21, E12, E01.
Maybe I asked you that.
Okay. All right. And so how does this now work for and so for PA1 and P of C, PA1 looks like this. A1, P of C, like this. So we want to say that this embeds inside that and E10, and there's a curve between E10s. Okay, so let's look at the combinatorial generator that's given by E11. E11 inside boundary BC, the action of E11 inside BC is just the point where you have slope 1, 1, well, all of those slope 1, 1. So this is just C. Now this has to map to something. Since the ECH cobordism map preserves the index, it has to map to an ECH generator, an ECC generator of, there's another lemma we prove which shows that this is a generator of ECH. But it's known for ellipsoids. We sort of bootstrap that to show it for convex toric domains. So what are all the generators of ECH index? So this has ECH index 4. ECH index equals the number of lattice points minus 1 times 2. Might have said something else. Sorry. And what are the ECH index 4 generators? It's either E10 squared, E01 squared, or E11. Now, the lemma we just proved says that since E11 is non-trivial, phi of E11 should be non-trivial, and it should have ECH index 4, so it has to be one of these 3 generators. Now this says the y coordinate of E11 has to be bigger than or equal to the y coordinate of alpha minus. So E12 cannot be alpha minus because the y coordinate is 2, and there it's 1. So this can only be E11 or E01. What are the actions of E11? Well, you can smoothly perturb this a little bit to see that the action of E11 in the polydisk has to be 1 plus A, and the action of E01 squared is 2A. And an assumption was A is bigger than 1, so 1 plus, so we need, for this anchored embedding to be true, we need that C is bigger than or equal to the minimum of 1 plus A and 2A, which is 1 plus A. So this proves C has to be bigger than or equal to 1 plus A. All right. So yeah, I think I'll stop there.
And can you get some information out about the existence of anchored embedding by looking at the filtration which you have on ECH? The non-triviality. So you have a window AB, another window AB, you have an embedding, and does the non-triviality of the ECH coordinate map tells you something about that.
Are you saying the filtration by the knot on here and by the
No,
knot?
no, no.
Oh, just the
filtration. I mean, there's a not so special, say, with
Yes.
orbits or whatever. So I wonder if you can see by the map in ECH, you have to study the windows, the actual windows.
It's not clear because they can.
Yeah, so maybe one doesn't get the full picture, but sometimes I have the feeling it has to tell you something.
I guess, but I think you change the question up a bit. Like the way we define anchored embeddings is by fixing the knots. But I think what you're saying is that if there is this non-trivial window, then you
Yeah,
exist.
so it would presumably be a statement about, if I do this for ellipsoids, about where the anchors would be the wave orbit itself. Does something go from a wave orbit to some other one and so on?
Possibly, but I guess we can't pin down which wave orbits, but we should.
Yeah, so maybe then one would have to enhance the theory, ECH by something, I don't know.
Yeah, I mean, one thing that's similar, we would hope, is if we look at just the filtration by the knot and then look at the sort of
I mean, by
capacity.
intersection numbers.
Yes, then maybe sort of those numbers being different can tell us something about obstructions. But we don't have any results there yet. One example that I would really like to understand is this one about so that's an example that's constructed either by folding or by toric mutation, and it doesn't seem like it's hard to construct anchors. Like our constructions are very naive in these cases, and like the obstructions are interesting, but in these cases we don't really get any obstruction nicely. So maybe there's some like interesting construction that we haven't found yet.
Oh, maybe I missed it, but so can you show the embeddings when you don't have the obstructions? I mean, you said that it's if and only if.
Yes. Yeah, when we don't have the obstructions, our embeddings are quite naive in the sense that you have, if a toric domain fits inside another one, then you have this cylinder between the E1 zeros or these. And then the other one was this, if between E01 and E10 is as long as the slope is bigger than -1, you can construct the surface. So these are all known as visible surfaces in toric domains. So those are the constructions.
Okay, so how do you construct the surface when the slope is? I mean, what is the surface?
I mean, so what you do is you pick for this one. You say that let's say this is say gamma 1, gamma 2. You just say that the pre-image in the torus is the 1-1 curve. So you just pick the 1-1 curve on these tori, and so on this end it's E10, on that end it's E01, and the slope condition is about it being symplectic. If you write down the conditions, you get this has to be.
And the condition that you wrote about the x plus y of the point, the slope.
That's exactly this condition that you can fit such a curve in there.